Alright, we're going to look at a classic example of a collision, and this is going to be an inelastic collision. And so what that means is it's not, right, think of elastic like a rubber band or a bouncy ball, and it's not going to bounce. But what's going to happen is energy is lost. And so our definition of an inelastic collision is where energy is lost in the deformation of our objects. In fact, this is actually a useful thing. Modern cars are built to crumple. If you ever go to a highway and you'll see the plastic barriers right before the concrete jersey barriers start, and sometimes there'll be empty plastic barrels. What's meant to happen is if you hit these, the collapsing of these will lose energy, to lose energy and momentum before you hit the solid divider. And so it's a design concept to have collapsibility or deformation where energy will go into the changing the shape of something. In our train example, the two things stuck together, energy would have to go into sticking them together, but a train couple is a very low energy collision. What we're going to do is we're going to look at probably one of the first uses of this, and it was within weaponry, unfortunately. But the idea is that we have a gun. And the gun is going to fire a bullet at some initial velocity. And we need to figure out how fast that bullet is going. And so what they used to do is they used to fire it into a stump of wood. So we'll give our bullet here in red a mass of the bullet and an initial velocity. And then we're going to give our piece of wood, our wood block, so wood, a mass. And we're going to suspend it from a pendulum bob. And what's going to happen is the bullet's going to fire, and it's going to lose energy ripping apart the wood. It has destructive energy that the bullet loses to the block, but it also transfers momentum. And so when the bullet gets embedded in the blocks, let's see, red to begin, blue, so I'll use yellow after. And so the initial is going to be this red and blue, and we're going to draw the bullet embedding in here in the block, and then we'll use purple. The block's going to grab momentum, and it's going to swing on the pendulum, and it's going to come up to here. There's a couple different ways we can measure it. Right now I'm just going to take the easy measurement right now so that we can see this. Right? We could look at it as a change in angle if we know the length that the bob is swinging on. What we'll do right now is we'll just focus on the change in height, and we'll learn to convert this to change in angle when we do this physically for real when you get back from turkey break. But so we're going to have to divide this into a couple of different phases. We're going to have a before the bullet hits the block and after the bullet hits the block moment. And then that's going to have a first half, and then there's a second half where the bullet has hit the block and the block starts moving. So what we'll do is we'll start over here, and we'll say initially the bullet has momentum, or the whole system has momentum. The initial momentum is the mass of the bullet times the velocity of the bullet plus the mass of the block times the velocity of the block. And it's going to have initial energy of the kinetic energy of the bullet plus the potential energy of the bullet. Well, there's no potential energy in this direction for the bullet, so that's a 0. And then the kinetic energy of the block, which is also a 0 at this point. And so the only energy is in the only thing moving, the only thing in any state of energy is the bullet. So the entire system has all of its momentum coming from the bullet and all of the energy coming from the bullet, because the mass of the block is 0. And so these terms 0 out. Now, the bullet's going to embed into the block. When it embeds into the block, the system changes its mass and energy, or momentum and energy. So the momentum is conserved. The P final is going to be the mass of the bullet plus the mass of the block, because they're wedged together, and some V of the system. I'll just call it V. And that's the final momentum. It's going to embed in here, and this is going to rise up after an embed. And then in the final energy, well, that's going to be when it swings all the way up to here. Right? Begins its transferred momentum, that turns into a velocity, takes the velocity, and it swings all the way up to here. And when it reaches that height, that's the final energy of my system. So we'll equate these initials and finals, since it's a conservative system. So, and our goal is to find the velocity of the bullet. Everything else is measurable, and we'll have some scale where we can see how high this is coming up. You'll see in practice it's usually easier to find the angle. Well, let's say we have some scale on the back here, and we can see how high our block has come to. So let's equate momentums. Let me do that in bright yellow. So the initial momentum is equal to the final momentum. And our goal is to solve for dB. And so I'll do a little change here. I'll put the ratio of the masses up front. And so this tells me the velocity of the bullet will be the ratio of the mass system times the velocity of the final system. But we don't have a velocity measurement here. So we're going to have to find the velocity by equating the energy of this system over here. So we know this is where we're solving for, and we figured out the transfer of momentum is going to give a certain velocity. But what we see happen to the system in its final state is that it's lost some energy into the deformation of the wood, and so that energy will come back out to the height it comes across. And we see that loss of energy in a loss of velocity term. We'll come over here and we'll equate our initial and final state of energy. Hold on 2 seconds. And let's look at this here. Well, what we want to know, let me change this here, I want the wrong subscript here, is what the velocity of this was at the beginning. Right, we know when it gets to the end up here, the block itself, right, we don't care about the bullet velocity, we care about the velocity. So this bullet hits it, it transfers all the momentum through it, and it immediately begins leaving with a velocity. So it goes from a 0 state to motion. When it reaches up here, the velocity is 0. And so this is our friendly conservation of energy that we did before. And so check your notes from chapter 7. But I'm going to say, with no loss, that the v at the bottom translates into the square root of 2gh. And so we can plug that into the v here, and our bullet is going to be going the mass of the bullet plus the mass of the wood block divided by the mass of the bullet times the square root of 2 times the acceleration due to gravity plus the height that the block goes to. And this was how they were able to find out the muzzle velocity of cannon shells, bullets in times when we had no radar or speed guns or anything like that. You would shoot into a mass and you would look at how the mass system evolved. And you would watch the energy transfer carry the mass system up, but the momentum kick caused the initial motion. And so this was a common way of finding the muzzle velocity of a projectile. And in the most general sense, it's one of the better ways of showing the conservation of momentum, or conservation of momentum and conservation of energy in an inelastic collision. Right? And we'll look a little deeper, and we'll find some systems that have elastic collisions. And I'm trying to hit the pause button, and I'm missing it. Sorry. There we go.